And we are live. Okay, so we are on volume. We are still doing volume. Covered a few shapes last week, and I'm covering a few more this week. The cylinder, the sphere, and the cone. That's what we are covering this week. Mostly I'm going to wing it. I have my things I've made out of paper and my tin cans from the pantry, etc. But then I started looking around, where's something shaped like a cone? And I couldn't find anything, and I didn't feel like making anything out of paper. So I didn't. I'm just going to do drawings. We're going to see how well I do with the drawing. Okay, there's the dog. Look at the camera, please, miss. There's the dog who doesn't know there is a camera there. I'm going to put her down. Oh, okay, lie down. Stay. If you're good, you get supper. Oh, she just grumbled at me. That's what dogs do, and they can't speak. But when you say things like, if you're good, you can have supper, they show you what they think. She says. Okay, so we have a picture of a cylinder, and we have a picture of a cone, and we're doing volume. So we're going to do volume of these shapes, and we're just going to try to make it interesting and think about what the volume formulas are really doing, which is a continuation, yes. Okay, I think I should get into it. Now, I don't want to have any props. I think drawings are going to be enough. So I've decided I'm not going to allow any cones or spheres or cylinders to make an appearance in the video. Hang on. Mandarin orange. Ah, the orange. The orange is a sphere. It's just a picture of an orange. I wonder if I can draw a picture of a sphere. As a math teacher, do I have the skills to do that? As an artist, but as a math teacher, do I have the skill? We'll see. Okay, so let's just get into it. The volume formula for the cylinder, that's what we're going to start with. So there's a cylinder. A cylinder is a prism. It's the only one of these three shapes that is a prism, and it is a circular prism, because the circle at the bottom is the same size and shape as the circle at the top. That makes it a prism, and therefore the the volume formula for any prism should apply. And what would that be? The volume formula for any prism is volume equals area of the base times the height. A little bit confusing at times because the height is the length of the tube. When you have your cylinder standing on a circle like this, then you can see, yeah, the 16 inches is the height. When it's lying on its side, it's not necessarily so obvious, so the length of the tube is the height. And then, of course, we have this formula that's not really a formula because it says area of the base, and the area of the base is the area of a circle. So I need the area of a circle formula to substitute into this position. And the area of a circle is pi r squared. So that's the area of the base. I have to multiply that by the height, and we end up with this pi r squared h. So a lot of people, a lot of math students will just simply memorize this formula and just always use it, but they're not necessarily thinking that it's really the same as this, because the area of the base is the area of a circle. Then we multiply by the height. It works. So that's interesting, and I think if you understand that this actually is a prism, and therefore this formula works and why it works, it makes you able to remember this better. I'm going to erase this upper version of the formula though, and as I'm going through my examples, I'm going to be using pi r squared h. We know what it means. Okay, so for this one, the radius is 7 inches and the height is 16 inches. It's actually drawn that size on my chalkboard wall. I want to try to draw things to their actual size, sometimes so that I'm not introducing the idea of a scale drawing into the geometry lesson, because I want the students to be able to focus on volume, which is what we're doing. And of course, we have started to check off our list, so I'm going to check off cylinder, because that's the first shape. We already have gotten into it. That's good. Okay, so pi r squared h, the radius is 7, the height is 16. Like all formulas, it's really not very difficult to use, because you just substitute for all of the values, and then you do algebra to simplify. And so r squared is going to be 7 squared, and then the h is the 16. I do want to respect my order of operations, very much so. When you have r squared and r cubed in these formulas, it is important that you know that and follow the order of operations, because you will get a wrong answer if you don't. So 7 squared is 49, I have to do that first. 3.14 times 49 times 16. And now I'm just going to grab the calculator to finish this off. 3.14 multiplied by 49 multiplied by 16 equals 2,461.76. Cubic inches, inches cubed. It is a volume. The unit is cubed. And then we have that other thing that we were doing last time, where we were looking at these formulas and seeing how we ended up multiplying 3 things by each other that were measured in inches. And we have done it again. It applies with all of these formulas. It always makes sense. It helps us to understand the formula. The pi is just a number. It doesn't have a unit. But the radius is given in this question with inches as the unit. And that happens twice. So there are 2 7-inch radiuses being multiplied by this 16-inch height. Inches times inches times inches gives us inches cubed. It makes sense. So you look at any of these formulas and you notice which of the things are measured in inches, and there will always be 3 of them. If it's a volume formula, it makes sense. Okay, 2,461.76. That's a pretty big number, but of course it's a pretty big cylinder, because a cubic inch is a pretty small little space, and almost 2,500 of them would fit into this cylinder, but that's a fairly large cylinder. It makes sense when you think about it. Volume has a tendency to give answers that make us think, uh-oh, did I make a mistake? My answer seems too big. When you multiply a number by another number and then multiply again, the way we always end up doing in these formulas, it ends up giving you a large answer. We should not be too surprised by that. Let's do a couple more cylinder examples before we move on to another shape. And my second one, I can't draw that. My second one is a radius of 2 inches and a height of 200 inches. That's a weird sounding cylinder, isn't it? So what I'm going to do is I'm going, hey, lie down. Lie down. Class isn't over yet. No supper yet. Okay, I'm going to erase this answer, and I'm going to erase this whole cylinder. I'll just write down the dimensions, because this is something I am not going to draw. So my second cylinder, the radius is equal to 2 inches. And yes, I'm keeping pretty much everything with inches in this lesson in order to allow us to concentrate on the volume concept of volume, and not to spend too much time trying to do conversions. And of course I am, again, as usual, using 3.14 as my approximate value for pi, because that is convenient. The radius is 2 inches, and the height is 200 inches. That is a very long cylinder that is kind of skinny. But it's, you know, does a cylinder have to be short? No, a cylinder can be very long. So when you think of it, even something like a wire is a cylinder. It's very, very long and very, very thin, but it's still a cylinder. So this volume formula would apply. Even the insulation around a wire, when you think of that, if you have that sort of rubbery insulation and the metal wire going through the center, if the metal weren't there, you would have a hollow cylinder. And it would be very long and quite skinny. So that makes an example like this make some sense, because there are some objects that we actually use that are very long, very skinny cylinders. Yes, there are wires and, you know, other things like that. Okay, so pi r squared h in this case is going to be 3.14 times 2 squared times the height of 200. Again, respect the order of operations. So 2 squared equals 4. We have to do that first. So my answer is going to be 800 pi. 4 times 200 is 800. but I have to multiply that by pi. 800 times 3.14 is going to be a little bit bigger than 2400. Interesting, the volume ends up not being that different from our first example. But let's finish it off. Get the calculator. 3.14 times 4 times 200 equals 2,512 inches cubed. Same thing happened. We know why. I'm not going to repeat that. So that's kind of cool. That cylinder that I had drawn before was rather large, kind of garbage canny sized cylinder. And it had a volume that wasn't very different from this. And then we talk about this extremely long, extremely skinny cylinder, but it has a very similar volume. That's kind of good. It makes us think about the shape and how flexible the shape is. As you vary the height, the length of the tube, and vary the radius, all sorts of things can happen that involve larger and smaller, and doing a lot of practice is going to make you feel comfortable with it. So that's my second example. I'm going to do a third example. I think what I'll do is I'll make some more room by writing my third example further over here. So the radius, make sure this fits on camera. The radius of my third cylinder is going to be 4 inches. And the height is going to be 12 inches. There, now I'm going to erase everything that I have over here. And actually, I think I want to draw this. Because I can draw this one. That long tube one would be inconvenient to try to draw. But this one is drawable. Let's see if I put it over here. Height of 12 inches. Well, this is a 12-inch ruler, so that's convenient. I'll draw that. Oops. Helps if you hold the ruler still. Okay. And then the radius of 4 inches means a diameter of 8 inches. So I'm just going to mark the 4. And there's 8. And then I'm going to put another 12-inch line here. Now, to draw this, I want to draw the arc of my circle on the bottom, and then I'll use a dotted line here. Not too bad. Draw this arc, and up here I don't need to use a dotted line, because if in a real cylinder this size we would see that circle. This one we wouldn't see because it would be down on a surface, I guess. And I like to show my radius. But I don't have to label the drawing with the sizes because I have them over here. And that's kind of interesting. 12 inches? Let's see here. Is this 12 inches? Oh, this is also 12 inches. Interesting. It looks like this cone is smaller, but actually it has the same height and the same radius. So the thing that makes this cylinder look larger is the fact that we see this sort of rounded part on the bottom, but we also see the rounded part on the top. But we're looking at the three-dimensional figure expressed with a drawing on a two-dimensional surface, and we can realize, okay, we kind of have to ignore some of that bulge at the top and the bottom. And yes, that is the full 12 inches, and so is this. Interesting. So, would they have the same volume? They seem to have the same height, which is 12 inches. I'll mark that here. And they have the same radius as well, this 4-inch radius. Yes, this is a 4-inch radius. Okay, so they're not going to have the same volume, are they? Let's do our volume formula for the cylinder first, because we are going to switch over to the cone. I know I put sphere in the middle, but I'm not doing the sphere next. I'm going to switch from the cylinder to the cone. So I will check off, I may as well check off the cone. There. Okay. So the volume formula for a cylinder, and we're not going to talk about this prism thing and the area of the base thing. We already know that. We're just going to write that formula that we've been using, pi r squared h. But because we're also going to do this cone, we may as well know its formula, which is volume equals pi r squared h over 3. Now, this can be written different ways, right? just how we arrange things. But this is the way that I'm writing it right now because I want to, because I'm making a point. Okay, so we realize that it looks like the same formula, except for this over 3 thing. It looks like the same formula because it is the same formula, and that's kind of interesting. But filling in this one, we're getting pi, r squared is 4 squared, and the h is 12. And following the order of operations, of course, pi times 16. 4 squared is 16. I want to do that first. And now I can just multiply it out, all out, and get my answer. 3.14 times 16 times 12 equals 602.88. The unit of measure for these dimensions was inches, so the unit of volume is inches cubed, and we know why. R times H, all of them inches cubed, that's good. Now over here, so we can sort of predict what's going to happen, can't we? The volume of this cone is going to be about 200, just slightly more than 200 cubic inches, because we can see what's happening in the formula. This is, of course, we're able to go back and forth between this cone and this cylinder because something convenient happened, which is I chose the same height and the same radius for both, but we're not going to get the same volume because the volume of a cone is 1/3 the volume of a cylinder. So long as the cone and the cylinder have the same height and the same radius, then the volume of the cone will always be 1/3 the volume of the cylinder. And this has been proven, and you can prove it yourself, and I encourage you to, where you could make, it's hard to find cones kicking around the house. Cylinders, there are lots of them. Tin cans, an empty tin can would be really good to do a little math lab and do an experiment with this. Let's say you have an empty tin can, and you'd be very careful that it doesn't have any sharp edges, of course. And you carefully measure its radius and its height. And then out of paper, it's not so easy to make a cone out of paper. I've done it, and it's a little bit of a struggle at times, but out of paper you make a cone that has the same height and the same radius as that cylinder. And then you try filling the cone with some good substance. Water wouldn't work if it's made out of paper, but sand, sugar, flour, not flour, too dusty. Sand, sugar, rice, uncooked rice. You fill that cone, and then you pour it into the cylinder, and then you fill it, and you pour it a second time, you fill it, and you pour it a third time, and what will happen is 3 cones full will fill a cylinder, because this is true. So you already know that it's going to turn out to be true, but it's still a really good math lab to do where you get your hands onto the items and you see. And doing this with different sized cones and cylinders would be interesting. So if you have several different cylinders of different sizes, different heights and radiuses, but each time you're experimenting with a cone that has the same height and the same radius as that cylinder, and you should be able to fill the cone 3 times and pour it in and it fills the cylinder, because this is true. Let's do this, let's finish it. We still have 3.14. We all know what's going to happen because it's not going to look very different than here. 3.14 times 4 squared times 12, which is 3.14 times 16 times 12, respecting the order of operations, which is 602.88, but I am not going to write a unit of measure yet because I still have to divide by 3. And this is the part where I will use my calculator, which conveniently already has 602.88 sitting in the display, so I'm just going to divide by 3 equals 200.96 inches cubed. Again, 2 R's and an H, inches cubed. Cubic unit. Cubed unit. Cubical unit. Okay, so that's interesting and it's kind of fun. And I was able to draw both of them, although the drawings are not perfect. So everything about this little lesson is beautiful and perfect except for the drawings. Not as perfect as I would have liked. So, any error is because of me drawing it. And that's just part of geometry. is that you often have to use drawings, and then it's hard to make a drawing perfect, especially if you're using a chalkboard and chalk. That's my excuse, and I'm sticking with it. Okay, I want to do another pair of cylinder and cone that have the same height and the same radius, but this time I won't bother with the drawings. I'll just list the height and the radius of both, and that leaves me more room for my calculations. I'll keep these two formulas here where they are. There. Although, actually, no, I'm moving this one over to the left a little more so that they're not as clustered together. So, volume equals pi r squared h. Make that look more like an r. Okay. Let's say we do it with some fun round numbers. So we will use a radius of 10 inches. Messy. Inches. And a height 25 inches. And with our cone, we will have a radius of 10 inches and a height of 25 inches. So we're doing it again, and it means that we already can predict what's going to happen. We're going to do this formula, and whatever answer we get, if we divide it by 3, it means we're doing this formula, and we will have answered both of them at once, sort of. Okay, so let's do that. Pi 10 squared, that's an easy one. We can do that in our heads. Times height of 25. Pi, respecting order of operations, 10 squared is 100. Times 25. I feel like continuing to do it in my head. 25 times 100 is 2,500. That's easy. 2,500 times 3 is going to be more than 7,500. But at that point, I want to reach for my calculator. 2,500 times 3.14 equals 7850. Nice round number, whole number. Inches cubed. There. Whole number happened partly because we used a rounded version of pi. If I used the real pi that's in the memory of the calculator that goes on, I would not have a round number answer. But it's fine to use 3.14 as pi. 3.14 times 10 squared times 25 equals 3.14 times 100 times 25 equals 7850. But I have to divide by 3 because this is a cone. Oh, there it is, still in there, divided by 3. Now I have a decimal, 2616.666. So I'm going to do round to the nearest tenth. 2616.7. 2616.7 inches cubed. Done. Okay, so these formulas are not very difficult to use. And we have the area of the base times the height, and we know that works because this is a prism. And then we don't try to make it work here because the cone is not a prism. It's not following the definition of what makes a shape a prism. Interesting. But knowing that this is always 1/3 the volume of this, so long as they have the same radius and height, kind of means that you have one less formula to memorize. If you were ever to memorize formulas, well, you just have to remember this fact. And if you remember the fact, then you say, oh yeah, it's that cylinder one. What's that one again? Oh yeah, it's this. I just have to divide it by 3 because I'm doing a cone. I like that. I like knowing how a formula is made and realizing it means I need to memorize less formulas. And in fact, I don't really have to memorize a formula for the cylinder either, because that's just the area of the base, which is the area of a circle, and I already have the area of a circle formula memorized. So the area of a circle times the height. So I don't have to memorize either of these formulas. That's what I like about this little branch of math. Okay, so enough cylinders. That is my 5th cylinder example I've done. My 2nd cone example, how much time have I used? I still have quite a lot of time left, that's good. I want to do more cones. So I'm going to stop doing cylinder and cone that have the same height and radius and just stop doing the cylinder and just do a cone. Because this answer keeps on being so anticlimactic because we already see it coming because we already saw the cylinder. So let's just do a cone without also doing a cylinder at the same time. We can also try this idea. What about a really tall, really skinny cone? Could that happen? Well, of course. If you have a very long height in your cone and a small radius, you're going to have a tall, skinny cone. So how about I try to draw one? Not 200 inches tall. I'll make it 24 inches in height. So how am I going to do that? Well, I'm drawing my height for one thing, which you can show in your drawing of a cone if you want, but a lot of cone drawings don't have the height drawn as a line. So if I want it to have that height, and what radius do I want it to have? I'll give it a small radius, I'll give it a 3-inch radius, which means I'm drawing a 6-inch diameter right now. It may be a little crooked, you know, angle-y wise, but now I want to connect. Okay, I'm almost there. But what I don't like about this now is it looks too much like a triangle. It's too much of a two-dimensional looking drawing. So in order to make it look like a cone, I'm going to draw that part here and then this dotted line part here. Didn't draw it perfectly. And I'm going to erase half of the diameter, so now we can see the radius. And what's kind of interesting is that if you do this, now this is a right circular cone, just to make sure what type of cone it is, because there is some variation with cones, but a lot of the ones that we're going to see are going to be what we call, well, the cylinders we've been working with, sorry for stepping off camera, the cylinders we've been working with have been right cylinders. And the cone that I'm talking about is a right circular cone. So more specifically, better, clearer name. This is a right circular cone, and that means this triangle actually has a right angle in it. But the height was 24 inches. So I'll write that here, I'll write it here. Height equals 24 inches, and the radius was 3 inches. And we can just go straight into our volume of a cone formula, which is V equals pi r squared h over 3, or if you will, the area of a circle times the height of the circular prism cylinder divided by 3, because it's not a cylinder, it's a cone. I'm just showing off how I remember this, because I don't really ever memorize this formula. I just understand that it's a modification of the cylinder formula, and I understand that the cylinder formula is a modification of the area of a circle formula. And I just think that's cool. Okay, pi r squared h over 3 is 3.14. 3 squared in this case, height is 24 over 3. I want to respect my order, and of course, how you simplify once you've substituted all the variables with values. How you simplify is partially up to you because algebra is flexible. But, of course, order of operations. So, first thing I want to do is turn 3 squared into a 9. And now, I have some flexibility in how I simplify this. And one of the ways that I can simplify it if I really want to is to cancel. If I cancel a 3 with the top and the bottom, that 24 turns into an 8, and the 3 cancels into a 1. So I just have to do 3.14 times 9 times 8. I know 9 times 8 is 72. 72 times 3.14 is going to be a little more than 72 times 3. 72 times 3 is 216. So I'm guessing I'm estimating an answer to 20-ish, maybe between 220 to 225. And now I'm going to get my calculator and find out what it actually is. 3.14 times 9 times 8. 226.08. A little bit larger than what I predicted. 226.08 inches cubed. Still have our RH, inches cubed. Fun. It's just fun. So I tried making, did a what if. I tried making my cone very tall and skinny, and the formula works fine. So that means I can trust that this formula will work with any cone, no matter how tall and skinny. So the traffic cone that you might see on the street someday, I can sort of try and find out what the radius and height of one of those would be. I bet I could find out by doing some sort of an internet search. But also the little tiny traffic cones that we use when we are practicing soccer. Yeah, you can use those too. I like those because they look like traffic cones, but they're for soccer. I don't know, I just find that fun. And where else do you see cones? Ice cream cones, not including the ice cream, but the cone. If you get the one that's actually shaped like a cone, because there are ice cream cones that are called that for some reason when they're not really cones. But yes, the ones that really are cones, they are available. So an ice cream cone, that would be, I wonder if I have any of those in my pantry, but I think not. I think not. It is springtime. Maybe it's about time. Where's my camera is my device that I use for my shopping list, so I don't want to go and try and put ice cream cones onto the shopping list right now, but I'll try to remember right after the lesson when it's time for me to feed her supper that I'll put ice cream cones and be ready for the summer. Okay, so that's pretty good. We've done how many cones now? 3? I look at the time that I've used and how much time. There's still quite a lot of time left, and I don't want to spend too much time on the sphere. So I think at least one more cone. We did 5 cylinders. Let's do at least 4 cones. I think this is the 3rd one. Okay, let's go. Let's make up any cone and find its volume. I have to erase that one. I'll erase all this stuff. I'll leave the formula there. And I promised that there would be no cylinders used in this lesson. But eventually we will get to this sphere, this orange sphere, or mandarin. It's a mandarin, flavor of fizzy water. So I have drawn cones, and I have to draw a sphere. Okay, maybe I should delay that as long as possible because drawing a sphere is hard. Okay, one more cone. What's interesting? Without getting too geometric, sometimes you're gonna get this. No, I already used a radius of 10, so I'm going to use a diameter of 30. How about 30? Diameter of 30 inches. That's big. It's a big diameter, well, 30 inches. It's pretty big. It's a pretty big cone. Bigger than the traffic cone. And the height, well, we tried having a really long height and a little tiny radius. So let's do the opposite. So a very large diameter, no radius, I didn't give a radius, and a height that's not so large. You know, it can't be 0, and I don't want to make it too close to 0, but how about a height of 10 inches? Okay, do I want to try and draw that? Not necessarily. I think I could though, but I don't want to. Okay, so I'm just going to get right into the formula, except I can't because this formula has R in it. I need the radius. I don't know the radius. Oh no, what will I do? When this happens, when you're answering a question, math question, someone's doing it on purpose. Some teacher is saying, I will provide the height and the diameter. And the student has to not only realize that the radius is 15, because I know we all realize that, the student should justify that. So the diameter is equal to 2 times the radius, but the diameter is 30, and we have algebra skills, so we substitute a 30 for our d in this little formula, and then we divide both sides by 2, so we can cancel and isolate our variable. Yes, we know how to do algebra. The radius is equal to 30 divided by 2, which is 15 inches. Now I can do this. Equals 3.1, actually, no. going to show you something else. Equals pi. Pi is a number. We don't have to turn it into 3.14, not right away, we don't have to. And I kind of like doing this too. Pi times r squared, which is 15 squared, times the height, which is 10. I still have to, over 3. Don't want to make that mistake. Wouldn't be the first time I've made that mistake. Okay. Order of operations, still keeping that as pi. 15 squared happens to be 225. There's ways of knowing that, one of which is be a math teacher and all the common sizes of radiuses that you will ever see, you will eventually memorize the squares of them and even the cubes of them. It just has to happen eventually. It's part of being a math teacher. Times 10 divided by 3 equals, I'm writing large, I'm going to run out of room. Pi, 225 times 10 is going to be 2250. But I still have to divide by 3. I'm going to go in this direction now because we all know that my handwriting becomes very messy when I get too low on the chalkboard wall. Can I do 2250 divided by 3 without getting a decimal? Because that's one of the reasons I'm keeping this pi instead of turning it into 3.14. Is to try to avoid having a decimal happen for as long as possible. 2250 though, it's going to give me a decimal. 2100 would be 3 times, 2100 divided by 3 would be 700. But I'm 750. Hey, let's double check this because I have learned my lesson. 2250 divided by 3 equals, yes. So this, if I do 2250 divided by 3, is pi times 750, or 750 pi. Which is a perfectly valid answer, and in fact I can even stick my unit of measure on. It's going to be inches cubed, isn't it? Inches cubed. 750 pi. Why would I want to do this? Because it stopped me from having to round pi. So this answer is so far very exact. But if I want to give a decimal answer, I have to convert pi into 3.14, or I have to round it to somewhere. I have to round it somehow, but I'm just going to round it the usual way and use 3.14. 750 times 3.14 equals 2,355. Is this going to fit? Inches cubed. And again, it gave me a whole number answer. I didn't have to round to get that, but it's still rounded because I used 3.14. So carrying your pi and converting it into a decimal only when you need to is a useful thing to do in math, and I like doing it sometimes. But of course, someone who wrote 3.14 right here would have still gotten the same answer as me, and they would be correct. It's starting to get a tickle in my throat, so I'm going to take this thing that is not a cylinder and drink some fizzy water. That's better. And now, looking at how much time is left, I think I need to go into the sphere a little bit. So the first thing I have to do is try to draw a sphere. I am about to perhaps be embarrassed. Erase everything except this list. Because I'm starting to deal with the sphere, I'm going to do two things. I'm going to put the formula for the volume of the sphere, which is volume equals pi, 4/3 pi r cubed. And we have encountered a formula where r is cubed. Cool. And it is cool. Okay, and then we think about that thing. Oh yeah, so if our sphere, well, let's choose a sphere and see if I can draw it. Oh yeah, I'm going to start by drawing a circle. So I'll choose a radius. And the thing is, that's all I have to choose. Because we don't have a height. A sphere doesn't have a height. We just have the radius. So as soon as you know radius, you have enough information to find the volume of a sphere. So, how about if we give the radius, let me think, radius, I'll have a radius of 6 inches. Which means what should I do? I can get my compass. I will get my compass. I'll draw it here. I'm just going to put a dot for the center. Then I'm going to take my ruler and my compass, and I am going to pull the two arms of the compass apart until they are 6 inches apart. Shorter than that. Shorter than that. Getting there. It's pretty good. Knowing that things are not going to be perfect when we are doing this on a chalkboard wall, we just decide at a certain point, okay, they are 6 inches apart, and it's going to give me a radius of 6 inches, which is a diameter of 12 inches, of course. So now I'm going to be careful not to pinch my two arms of my compass together, or pinch them apart. I'm going to be careful to keep this 6-inch radius, and I'm going to keep on doing this until I make a mess. Yes, until I make a mess. Not too bad though. Now, that's a circle. How do I make it look like a sphere? Well, I only have 2 tricks for that. This dot doesn't help, so I'm getting rid of it. One is to draw that little sort of reflection, but give the reflection, which is kind of like a rectangle, but you curve the sides of it so that they mimic the arc of the circle itself. So that's supposed to look like light is shining on it. How well is that working? And then the other thing is now to give it a shadow. How's that? Give the shadow look a little more round, because of course the shadow of a sphere, we would expect it to be round, wouldn't we? I don't know if I'm making it any better by fussing over it like this. Let me look on the tripod's in the way, so I can't see my own drawing. I'm just going to have to hope for the best. There, that is my best attempt at drawing a sphere. A representation of a 3-dimensional shape drawn on a 2-dimensional surface. Big part of geometry. Volume of a sphere, volume of that sphere, which is meant to be life size, if you will. It has a radius of 6 inches. So what's its volume going to be? Its volume is going to be 4/3 times pi, which I'll convert right now into 3.14, times 6 cubed. So the people on more beginner levels of math would say 6 cubed, the only way to explain that is 6 times 6 times 6. But of course, we can handle this. 6 cubed, we know how to use buttons in the calculator. Well, which buttons? Some calculators do not have an x cubed button. This one does though. So 6 cubed, I already know it's 216. Same reason that I said before. I've memorized it because I've done this so many times with all sorts of common numbers in this position. So I happen to know that 6 cubed is 216. In this calculator I can do 6 and then hit x cubed and then hit equals 216. And I have to do that first because I am respecting the order of operations. I can also just, I'm now at this point, I can do anything I want in terms of the order in which I simplify. I can cancel this 3 with the 216, which happens to be at least exactly triple the number 72. But I can do it any way I wish. This time I will do 4 divided by 3 times 3.14 times 216 equals 904.32. Inches cubed. Keeping an eye on the time. And the r is cubed. It's kind of really quick to notice that. 4/3 is a number, it doesn't have a unit. Pi is a number, it doesn't have a unit. But r is the radius, and it has a unit, and the unit is inches. But it happens 3 times, which gives us that little 3 up here in our unit of measure for our volume. Not very difficult, because although the formula, it might be hard to remember this formula sometimes. If you don't use it very often, then you'll have trouble remembering it. But the good thing about it is the only thing you need is the r. As soon as you know the radius of any sphere, you're able to find its volume. So any ball, if you can find the radius. It's not so easy to measure the radius of the ball. I tried to do that recently. The ruler won't go into the middle of the ball, so it's hard to be exact. But you can do things like, for instance, if you have a standard size 5 soccer ball, for instance, you might be able to go online and do a search and find out for sure what the radius is supposed to be for that size of standard soccer ball, and then you'd be able to just plug it into this formula, because the radius is all you need with the sphere. Radius is all you need for the volume formula of the sphere. The radius is all you need for the surface area of the sphere, and as we all know, the total area of a sphere is the exact same thing as the lateral area of a sphere, because it's a sphere. And now I have checked off my last shape. So, the time I have left, do I want to do another example of a sphere? I don't want to try to draw another sphere necessarily. Do I want to do another example when it's so straightforward? Whatever the radius is, you cube that. Do it first. You multiply by pi, multiply by 4/3, or multiply by 4 and divide by 3. And you will have your volume. So what I want to do instead is do one cylinder, and then the volume of a cylinder, and then do a cone with the same height, but not the same radius. So I'm stretching things a bit, but with the same volume. Yes, and then if I'm going to have a cylinder and a cone that have the same volume, I may as well also have a sphere that has the same volume. So this is where I am marrying these three shapes together into a, I won't call it a word problem, into a situation. Yes, it's a situation. It's complicated. Okay, so I will erase everything except my list of shapes. I'm even erasing this beautiful drawing. And I said that I wouldn't bring any cylinders, props, but I may as well use this one. Should I use this one? Or should I use this one? They're both made out of standard 8.5 inch by 11 inch sheet of paper. I'll use this one. I'll use the skinnier one. So, I'm not going to draw it, because you can see it. I don't have to draw it. That's the good reason to have props, is so that you don't have to draw them. So, cylinder. I'll do cylinder here. Ooh, exploding chalk pieces. Cylinder. The height of this cylinder is 11 inches. It's convenient. And the radius, I think I'm going to have to measure the radius. I could calculate it to find the exact radius, but I don't want to, so I'm going to use an estimate. And this one, the diameter looks like 2.5, so I'm going to call the radius 1.25, 1.25 inches. There. So I'm going to find the volume of this cylinder, and then I am going to find the volume of, well, no, I'm going to find the radius of a cone that would have the same height and the same volume. So I can't do that, and I'm going to find the radius of a sphere that would have the same volume. That's a little bit challenger question at the very end of the homework-ish, but we are getting to the very end of the lesson, so I guess that's okay. Just doing this for fun, because it's interesting. It's thought-provoking. I want to provoke some thoughts. So the volume of a cylinder is pi r squared h. And so the volume of this cylinder is pi times r squared, which is 1.25 squared, times the height of 11, which is pi times, I'm going to do 1.25 squared in my calculator. 1.25 times 1.25 equals 1.5625 times 11. At this point I just have to multiply. So the 1.5625 is still sitting in there, times 11 times 3.14 equals 53.96. I'm going to call it 54. So I'm rounding to the nearest unit. 54 inches cubed. RRH, inches cubed. Now I'm going to switch to the cone. So I'll do the cone. How much space am I going to use? I'll do the cone here. The volume has to be 54 inches cubed. I don't need a calculator in my hand right now. And the height, I want to keep the height the same at 11 inches. I'll write in for inches there. I should really do that more often. There, in. I hope I'm not getting people confused with those little inch symbols that just look like scribbly marks and the teacher is being messy. Okay, so we can predict something, of course. We know it's the same volume. We know it's the same height. Is the radius going to be more than 1.25 or less than 1.25? Think about that. The volume, I'll do the volume here. I'll try to leave room for the sphere over there. Volume equals pi r squared h over 3. The volume is 54 equals pi times r squared times 11, running out of room, divided by 3. Now we have an algebra question with r squared. Interesting. But we can do that. We can do algebra. I know how to do algebra. So I'm going to multiply both sides by 3. Well, I'll cancel that 3. And 3 times 54 is 162. Yes, 162 equals 3.14 r squared times 11. So I'm going to divide 162 by 3.14 and by 11, which I'm doing on both sides. Cancel, 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 cancel. My r squared is isolated. Is this fitting in the video window? Yes. R squared, 162 divided by 3.14 divided by 11. 162 divided by 3.14 divided by 11. 4.7, again there's some rounding here. Therefore r, the radius, is going to be, is this fitting? Can't tell. Yes it is. The radius is going to be the square root of 4.7, which is going to be 2.167, I'll call it 2.17. 2.17 inches. I'm using that little inch symbol because I'm tired of writing that below on the chalkboard wall. So it's bigger. So the radius of this cone has to be bigger than the radius of this cylinder in order to make it able to have the same volume and the same height. And now we're going to do the sphere. Sphere. And that's complicated because we're trying to isolate r cubed in our algebra, and I don't know if we've done that yet. But it can be done, and there are buttons on the calculator which you will eventually have to use even if you don't know how to use them yet before you get to this question. The volume is 4/3 pi r cubed. The volume, I wanted the same volume, remember. The volume is 54 equals 4/3 pi r cubed. Therefore, my r cubed is going to be equal to 54 times 3 divided by 4 and divided by pi. I apologize if this is looking cluttered, and I am going to run out of room. I'm really good at running out of room when I do calculations. 54 times 3 divided by 4 divided by pi. 54 times 3 divided by 4 divided by pi. I'm putting the 3.14 for the pi. 12.89, I'll call it 12.9. So my r cubed is 12.9. I have to do in this calculator, oh, it has the x cubed button and it has the cube root button, so it's kind of easier with this calculator. Not all calculators have that, but scientific calculators always have the y to the x button. And you can use that for this. And the second function that goes with it. Calculator class, okay. R cubed equals 12.9, so what I'm doing is I'm doing second function x cubed, which means I'm doing cube root of, and then I do 12.9, and I hit equals, and then before we look at the answer, how big a radius would a sphere have to have in order to have the same volume, 54 inches cubed, as this cylinder and that cone? The radius is going to be larger than 1.25 inches, and it's going to be larger than this 2.17 inches, isn't it? 2.345, I'll call it 2.35. R equals, I don't have enough room, R equals 2.35 inches, not inches cubed, inches. It is bigger. If I had time, I would draw all three, because that's kind of a useful thing to do right now. Draw a cylinder with this height and that radius. Well, I don't really have to draw that one, do I? This cylinder, we can see how big it is. We can see its volume. This empty space that you see in the middle of it is its volume. So that volume is the same volume as this cone with the larger radius, but the same height. Same volume. And then the sphere. How big is a sphere? A radius of 2.35 inches. That's a diameter of 4.7 inches, which is not the same size as any of the sports balls that I've been using as props during this geometry unit. Bigger than a lawn bowling ball, quite a lot smaller than my soccer ball, is what I would say. But it's kind of interesting to picture that. And it's fun to experiment with. And like I say, this is a good area of math to do the math lab. Cylinders that you can make out of pieces of paper. Cones that with a bit more trouble you can also make out of pieces of paper. Spheres, well, you know, various fruits and sports balls will help you with that. Cylinders are so easy in the pantry. But we were talking about the triangular prism and how few of them there might be in a regular household. Well, the cone, another shape, don't see that many of them kicking around in your normal household. All of it's interesting. Think about the formulas. Think about what the formulas really do. Think about the fact that the volume of a cone formula is really just the volume of a cylinder formula divided by 3. Think about the fact that the volume of the cylinder formula is really the area of a circle formula times the height, because it's a prism. And think about how the sphere is special because the R is the only thing you need, and you can find out anything you need to know about a sphere. That's all interesting. And I'm very interested. She's interested too, but she wants her supper, so I'm going to pick her up so she can say goodbye, and then I am going to say goodbye too. Thank you very much for being here. It was fun. Okay, supper time. Up you go. You're well rested. You're ready for the great expenditure of energy that will be associated with eating your supper, aren't you? So you and I are alone. There's no large group of people inside that little device. We have our privacy. We're just talking about supper because, you know, we're both hungry, right? Right? She's very patient with me. I will see you next time. Goodbye.